Okay, so we come back to the electronic properties of N-type zirconium cobalt bismuth. Sorry, we have to. Okay, yes, it's we would like to talking about the electronic properties of negative type of zirconium cobalt bismuth. The negative type nickel-doped zirconium cobalt bismuth-based materials were prepared by the ball milling and hot pressing method. All the samples are single phase. You can see figure S3 and highly dense. The major electronic properties of the N-type zirconium cobalt bismuth-based have Houston are shown in figure 4. The undoped ZCB shows a low electrical conductivity, and after nickel doping at the cobalt site, the electrical conductivity is sustainably improved. You can follow the figure 4a. Such an enhancement should be mainly attributed to the increase of whole carrier concentrations. As shown in figure S5, the carrier concentrations increases monotonically with the nickel concentrations. This indicates that nickel is an efficient dopant for supplying electrons to ZCB. Similar to the case of ZCB, similar to the previous research. Accordingly, the Seebeck coefficient of nickel-doped ZCB decreases with the increases of nickel concentrations. You can follow the figure 4b, with the exceptions of the undoped ZCB. By optimizing the carrier concentrations, a reasonably high peak power factor around 27 can be realized by 0.1% of nickel doping. The power factor of positive bismuth of ASN doped is also plotted for the comparisons, and it is noticeably higher than that of the negative type bismuth over all the whole temperature range. The average power factor between 300 and 1973 Kelvin can be calculated by the integration method, and it is around 20.8 for negative type, and as high as 33.6 for positive type. Such a marked difference in the power factor between the N-type and P-type ZCB-based material should be mainly ascribed to the difference in band degeneracy and pocket shape between the conduction band and valence band. Therefore, despite the similar inertial effective mass between the N and P-type ZCB, the density of stakes effective masses of P-type ZCB-based material are notably higher than those of their N-type counterparts. Because the inertial effective mass are comparable between the N-type and P-type ZCB, the carrier mobility of the P-type ZCB-based material remains similar to that of their N-type counterparts. To further reveal the effect of electronic structure on the thermoelectric properties, we calculate the product of carrier concentrations and the square of Seebeck coefficients for ZCB-based materials, as shown in figure 4d. it can be observed that Seebeck coefficient squared times concentration value of the p-type DCB is sustainably higher than the its n-type counterpart over the whole temperature range. And next, we will move on to the thermal conductivity of the n-type DCB. Thermal conductivity of the n-type DCB base half Husler is shown in Figure 5. The room temperature thermal conductivity of DCB nickel doping DCB is reduced considerably with the increase of nickel concentrations. The room temperature's thermal conductivity of undoped DCB is around 8.9, and it's only around 4.3 for nickel doping DCB, a reduction of around 52%. This can be attributed to the high concentrations of substitutional point defects. For example, like nickel at the cobalt site, that disrupt the phonon propagations. To reveal the phonon scattering effect by nickel doping, we further calculated the thermal lattice conductivity, as shown in Figure 5b. The room temperature lattice thermal conductivity is around 8.9 for the pristine DCB, and it is around 3.4 for nickel doping DCB. A reduction of is around 62%. In addition to the nickel doping, thermal conductivity can also be largely reduced by alloying DCB with DCS, compared to the heavy nickel doping that leads to the inferior power factor. Alloying DCB with DCS can effectively reduce the thermal conductivity while maintaining a relatively high power factor. So we're gonna talking about the ZT and the conversion efficiency of the n-type DCB. The dimensionless thermoelectric figure of Murray ZTE of the n-type nickel-based nickel doping DCB is shown in Figure 6a. Evidently, nickel doping can effectively enhance the ZT, and the peak ZT of around 0.74 can be achieved by nickel 0.1 nickel doping at 973 K. By further allowing nickel doping DCB with DCS, the thermoelectric performance can be further improved, and a reasonably high peak ZT of around 1 at 973 Kelvin can be optimized by nickel and SB co-doping DCB. To demonstrate the reproducibility of the result, we prepare 4 different batches of this compound. The major thermoelectric properties are similar between the different batches, and the ZTs are quite comparable. To demonstrate the asymmetrical thermoelectric performance of DCB-based materials, we also plot the ZT of p-type in Figure 6a for comparisons. It should be noted that the thermoelectrical performance of the n-type is noticeably better than that of the n-type over the whole temperature range, which is a good agreement with our predictions. In addition, comparisons of a nickel and asymmetrical dope DCB with other state-of-the-art N-type half-Hauser materials is also made, as shown in Figure 6b. Although the NS-based material shows a high ZT in a lower temperature range, their ZT is reduced at elevated temperature due to the bipolar effect. In constraint, the ZT of nickel and asymmetrical dope ZCB increase monotonically within the study's temperature range, and therefore this compound is comparable with the NS-based materials at elevated temperature. In addition, this compound shows noticeably better thermoelectrical performance than all of the other N-type of half-Hauser materials for overall the temperature range. It will be noticed that the DCB-based compound can achieve ZT around unity at 973 Kelvin for both carrier types. It should be noted that the ZCB-based compound can achieve ZT around unity at 973 Kelvin for both big carrier types. This makes the ZCB compound highly promising for mid and high temperature thermoelectric power generations. To evaluate the potential of ZCB-based materials for the thermoelectrical applications, we measure the heat-to-electricity conversion efficiency for the single leg of nickel and asymmetrical doping ZCB. A maximum efficiency of around 7.9% can be obtained at the cold side temperature of around 300 Kelvin and hot side temperature of around 950 Kelvin. The reported conversion efficiencies of P-type single leg ZCB is plotted in Figure 6.6 for comparisons. A unique couple of N-type DCB and P-type was further prepared. The dimension of each leg was optimized by considering the difference in electrical resistivity and thermoconductivity between the materials. Our result shows that the maximum heat-to-electricity conversion efficiency for the unique couple can be as high as around 10% at cold side temperature of around 300 Kelvin and at the hot side temperature of around at 983 Kelvin. So we're now moving to the discussion part. We have identified the relationship between the asymmetrical thermoelectrical performance and the weighted mobility ratios. The weighted mobility ratios depends on the difference in electronic structures and the different scattering of carriers. The thermal stability difference may also lead to the asymmetrical performance in real applications. For example, the low stability of the iron-based P-type of sculptures is a major limitation for achieving high efficiency in these modules. The relationship for achieving high efficiency in this module The relationship between the asymmetrical thermoelectric performance, and the weighted mobility ratios can be used to predict the thermoelectric performance of the materials. However, it should be pointed out that the realizations of both N-type and P-type of semiconductors heavily depends on the dopability, which relates to the solubility limit and the defect level. For example, shallow level or deep level of the dopants. In addition, identifying and controlling the intrinsic defect that means the Fermi level will be equally important for realizing the bipolar doping. Therefore, the prediction of thermoelectric performance of unreported materials via the weighted mobility ratio can be roughly considered as an upper limit. In this work, the thermoelectric performance of several materials has been predicted. Experimentally, we have prepared the N-type of ZCB base of half-Husserl by optimizing the carrier concentrations and reducing the thermal conductivity. A peak ZT of around 1 at 973 can be achieved for nickel and asymmetrical doping. Compared to the state-of-the-art N-type ZNS-based half-Husserl, the ZCB-based material demonstrates comparable thermoelectric performance at evaluated temperature. In addition, the ZCB-based material outperformed of the other N-type half-Husserl over all the temperature range. The heat-to-electricity conversion efficiencies is further measured for a unit couple consisting of the N and P type of ZCB-based material. A maximum efficiency of around 10 can be obtained at the cold side and the hot side temperature. Our work demonstrates that the ZCB-based half-Husserl materials are quite promising for mid and high temperature thermoelectric